sorry, like this guy keeps popping up on the Wi-Fi. Okay, so why cold molecules? I'm not going to go into the motivations of why I want to do cold molecules, but I would just want to kind of survey the field really quickly. And by far the most successful way has been magneto association of bialkalis. KRB and NAK have both reached quantum degeneracy and been able to study dipolar evaporation, collisional shielding. But my hope is with laser cooling molecules, we can actually explore a much broader range of molecules and push these guys into the nanokelvin regime. And this list is by far not exhaustive of the field. We have many other molecules that are being laser cooled, and I hope to hear very exciting talks coming on so I can add to this list. So email me and tell me to put this in here for the next, make sure I have a complete list for the entire field. Sorry, the Wi-Fi keeps popping up on this computer. Okay, so what's the passive current laser cooled molecules? So we have molecules in magneto-optical traps. We can laser cool them, put them into conservative traps. So what do we want to do right now? So number one is trap tweezers arrays. The density is already good enough for this. I hope to hear exciting talks. I'm not going to steal people's thunder on this, so I'm going to move on to what we want to do in YO. And YO, what we really want to go is towards quantum degeneracy. And so there's a lot of molecules already trapped with pretty high phase space density. So this is our lattice strontium fluoride ODT that we just heard about. We're sympathetic cooling to get things colder. But so far, the highest phase space density has been in YO at 3.1 times 10 to the minus 6. This is in a lattice, not very conducive for bulk gas studies if you want to do evaporation. But I'm proud to be in this field, though, because it wasn't like 8 years ago when I was like still in high school where people finally started capturing these guys. And I want to thank like strontium and calcium fluoride specifically for doing like tremendous work, like bringing this into a reality. And this is a plot I like to call Yehweh's Law, which was a grad student. And we'd, every time a new paper came out, we'd be like, oh, wow, that's great. We put in new things. And I hope to keep this trend going. And throughout this talk, I hope to convince you that with YO, I want to keep pushing this and hopefully maybe do a nice quick turn up at the end. So by the end of this, everybody's going to be an expert in YO level structure. So if you want to start a YO experiment, here's a pretty good primer. But what we want to do is choose a nice molecule with good Frank-Condon factors and a strong transition. And we want to exploit that two-level system that was described in the previous talk, right? The ground state. So this is great. YO has a little bit of interesting problems, though. So YO kind of has a unique level structure compared to the other laser-cooled molecules going on. And what happens is the nuclear and electron angular momentum actually couple to each other before they couple to the internuclear axis. And we get these two interesting quantum numbers called G. You'll see this all the time in different molecules that have large Fermi contact interactions. And what this does is creates a very interesting singlet and triplet states separated by a very large frequency gap. Okay? And so these guys are pretty well isolated from each other. But the thing I really want to talk and focus about is this particular G factor right here, 0.012 on G0 F equals to 1. I want you guys to keep this G factor in your mind throughout this talk. Okay. Another interesting thing about YO is it has this interesting delta state sitting here. Well, that's pretty interesting. What's going on with this guy? Well, unfortunately, this guy actually can couple to the pi state through spin-orbit coupling, and it actually ruins this rotational closure that I claimed you needed for molecules. And so this was actually a horrendous hindrance on YO in the early days because we had to plug all these holes in N0, N2, V1, V2 all the way up the ladder. This is not great, but we've gotten to the point YO we can fix this problem. And I'm going to show how like this unique structure, particularly this triplet, these G factors and these delta states are going to help us all throughout the rest of the talk. So what's the state of the art of YO like a year ago? Okay, so we would trap in a dual frequency MOT proposed by Tarbit's group, where we put on blue detune and red detune beams with the correct polarizations for our given quantization axis to repump all these type 2 transitions. Then what we could do is we did an interesting thing where we could cool and compress by alternating between rum and assisted gray molasses. People call it lambda enhanced gray molasses. You'll read it. We could cool and compress this guy down. We can get it very cold very quickly. And then what we could do is we could cool while loading this guy into a conservative trap, and in the trap we can cool. And so this was the state of the art that we had in the experiment. We could trap only about 1,000 molecules in lattice. This looks good, great. But I'm going to be realistic on why can't we do better, right, in the field. So number one, as you know, the number of molecules is low compared to atomic species. There's groups here that can trap like 1 million molecules. We're not quite there on YO. But in the last year, we actually significantly increased the number of molecules we trap into our dual frequency MOT by improving slowing. But I'm not going to concentrate on that today. But if you want to ask questions, I'm very much happy to talk to people throughout the talk on it. The thing I want to concentrate on is this. The molecular cloud is too large to efficiently load from into a conservative trap. And what do I mean by that? I have this little cartoon I got for you guys where the blue is like GMC cooling and the red is symbolizing like a dipole trap here. And so the problem is there's really no position-dependent force outside roughly the beam waist for these molecules to fall in. We basically completely rely on random walks in this guy in the gray molasses to fall into this trap. And this is not good. This is terrible loading efficiencies only on the few percent level. And so to be very serious about this, if we want to get to quantum degeneracy, we want near unity transfer from this step to this step. And I'm going to talk on this, the rest of this talk, and how I'm going to do this. And what we want to do is we want to take this cooling and compressing mechanism, and we want to put it into one physical mechanism here. Okay? So we're going to talk about results on two things. The Bluetooth magneto-optical trap, I'm going to show lots of results on. So what we want is a very strong sub-Doppler force, which we already know GMC works very well. And we want to put on a position-dependent scattering force. So we're going to turn on a quadrupole field with this guy. And then the next thing I want to talk about is a narrow line magneto-optical trap using this delta state. So I will say this guy's tricky and complicated, but I will say my colleagues 10 meters from me in strontium do this every day, and they directly laser cool to phase space densities of 0.1 directly before they start their evaporation. Let's maybe do a little bit of Bluetooth magneto-optical trap theory and remind people kind of what's going on here. So we have a little table kind of describing the difference between type 1 and type 2 transitions. Type 1, you're ready tuned, you have cooling, Doppler and subdoppler, heating when you're blue. Type 2, below a critical velocity of a few meters per second, around tens of millikelvin level, you're actually going to have cooling if you're ready tuned for Doppler, and then you're going to have subdoppler heating. But more importantly, if you're on a type 2 and you're blue detuned, you're going to have heating and you're going to have subdoppler cooling, okay? And this cooling is known as gray molasses, right? And so this is extremely efficient and relies on non-adiabatic induced transitions through polarization gradients. This cooling is a beautiful mechanism. I'm not going to go into a lot now, but in my opinion, it's probably one of the most beautiful mechanisms in atomic physics. It's extremely efficient, and it does exactly what you wish a cooling mechanism to do, and it works very well for molecules. Okay, so what's the next thing we need? Well, we want to turn on a quadrupole field. And you may be saying, well, Justin, in atoms, if you turn on an offset field, even of a Gauss, you're going to completely ruin your subdoppler cooling, right? Well, that's true, but it's known, theoretically and experimentally shown, that GMC is very robust against perturbing B fields, okay? And this is required for the MOT. And this is especially true into YO. And this comes back to that unique level structure, that small G factor I pointed out earlier on G0. So here is some data from our PRX paper, and I just want to show that up to offset fields of 25 Gauss, we remain 3 times below the Doppler limit in YO. So YO is completely amiable for this type of cooling and trying this Bluetooth tuned MOT, okay? So how are we going to do this? I don't want to blast people away with level structure, but this is basically the polarizations and detunings we use for a dual frequency MOT. So for a given detuning and quantization axis, upper state G factor sign and upper and lower quantum numbers, you can choose the right polarization for your restoring beam. And this is what it is for YO, for a dual frequency MOT. And so to go into a blue detune MOT, all we need to do is turn off these guys. We don't want any red detune components. And then we're already halfway there. We already have one blue detune component on G1 to do these triplet states because we use the dual frequency mechanism. And then the only thing we need to do is jump to detuning blue and flip the polarization, okay? So this is what we're going to do for a blue detune magneto-optical trap. And I'm going to define L1 as the detuning from G equals to 0, F equals to 1, and L2 as the detuning from G equals to 1, F equals to 2. And I'm proud to say it doesn't happen very much on the experiment, but it worked first try when I tried this. So what you're looking at is a picture of a blue detune magneto-optical trap of YO after holding for 200 milliseconds. The radial size is 260 micron. The axial is 198 micron, and this is the number density in this image here. And just as a comparison on the raw image data, this is the comparison between our dual frequency MOT and density here. So it's 50 times more dense than our dual frequency MOT, which is very exciting. And so I hope to kind of allude to kind of like this beautiful symmetry actually between a three-dimensional gray molasses and a blue-detuned magneto-optical trap here. And it seems the game is really, you want low excited state population for efficient subdoppler cooling, but it needs to be just high enough to have that position-dependent spring force. You need to be able to scatter photons to recover a spring force. And so you can see here that even at 170 milliseconds, we only have about 2.5 trap oscillations. But due to a number of technical improvements that we're going to go through, we can hold our magneto-optical traps to like our vacuum lifetime at this point, and which we're going to get into. So maybe we can try to pull out a couple interesting physics. I will say this data is like very hot off the presses before this conference, but I'm going to go through what I think the understanding is, and hopefully everybody can pitch in. So what you're looking at is we detune L1 about half a line width, and we detune L2 about half a line width, plus this very specific number of 264 kilohertz red detuned that we're going to get into. And then we ramp the B field up to 4 Gauss per centimeter, and this data over 40 milliseconds we hold for 100 milliseconds. And so what you're looking at is just the temperature in the radial and axial directions, and then the size. So the temperature is increasing with intensity, and this is exactly what we expect. We expect the momentum diffusion constant to increase with intensity, and we expect alpha to be pretty intensity and detuning independent. But interestingly, the size is also increasing, which is going to have some pretty interesting consequences on the spring constant. But you might notice like there's this hook and dip up when we get to very low intensities, like the temperature is increasing. Well, that's kind of interesting. But Bill Phillips and Jay Dalibard kind of did like a full simulation of 3D optical molasses, and they also claim the same thing. They say that you're going to get to a certain intensity, and then the cooling is simply just going to break down, and you're actually going to get more spatial momentum diffusion in your temperatures, so it will increase. So that's pretty plausible, possibly, for what's going on for this. Next thing we can do is look at the spring constant. So we can take the average temperature from the data on the previous slide and use Oka partition. We see a pretty interesting thing happening here, that the the spring constant peaks and then starts decaying with higher light shift. And from this, we have a peak period of 73.91 milliseconds, which alludes to that blue detuned magneto-optical trap slide I showed you earlier of the time evolution in this guy. And what we can do is we can also plot the damping rate just by getting the scattering rate at each intensity and then using this relation here. We see that the scattering rate is off by a factor of 3 compared to the dual frequency MOT, which is exactly what Tarbit saw in rubidium, so that matches pretty nicely. But we also see alpha kind of peaks and plateaus. This is actually what we do expect. We actually expect alpha to be pretty intensity independent. For the decay of the spring constant, well, there was simulations by Wallace where they came in and they tried to measure the spring constants in rubidium, and they also claimed that in a 3D molasses, as you increase the light shift, they also say that the spring constant should be decaying. That's plausible, I would suppose, with this data and their simulation. And the dashed lines you're seeing is what 1D sigma plus sigma minus molasses theory would predict, where alpha and k are going to be directly proportional to each other here. Another quick thing we can look at is the common detuning scan. There's not like a whole bunch of interesting physics going on here. It decays exactly as you expect. Roughly 1 over delta-ish, not quite steep enough over here to be 1 over delta. But basically we find like a common detuning L1 and L2 from these manifolds that gives us an appreciable spring constant and keeps us cold. That's pretty great. Now we get to a very, very interesting set of data. And I'm going to call this the differential detuning on L2 here. And so what we're doing is we're just setting the common detuning between L1 and L2 fixed, and then we're going to dither around L2 at different detunings. And 0 is going to be 2-photon resonance, right, for a lambda-enhanced gray molasses. And what you're going to see is that the temperature in the radial direction is decreasing as we get closer and closer to a 2-photon resonance here. The axial is plateauing, but the axial has a field gradient that's twice as high, so I would expect this guy to actually decay slower. And if we look at the size, we see something very interesting. We see as we go further away from 2-photon resonance, the optimal position is increasing decreasing in effectiveness, and our size is increasing. But as soon as we go to 2-photon resonance, our spring constant is disappearing. Okay? And so we can actually just plot the spring constant, and we see that as we go to 0, 2-photon resonance, spring constant disappears, and as we go away from 2-photon resonance, we get a spring constant back. And so it seems, right now is what my understanding would be, is like there's this kind of deep symmetry between a 3D gray molasses and a Bluetooth magneto-optical trap. So by going to 2-photon resonance, you can create a very coherent dark state and eliminate the excited state population. But as soon as you go away from 2-photon resonance, you destabilize that dark state, and you can get an appreciable spring constant back. So you can just, by sweeping the tuning in different parameters, you can just go completely into the molasses or right into a Bluetooth magneto-optical trap, is what my current understanding would suggest. And so what is this? So what's kind of the overview of this guy going on here? Well, we have the first sub-Doppler magneto-optical trap of molecules, as far as I know. Hopefully, maybe somebody might come in and say, but we robustly remain 2 to 3 times below the Doppler limit at all parameters that we scan out. It's a couple orders of magnitude better than any magneto-optical trap in phase space density. Depending if somebody loads millions of molecules, I hope to hear very high numbers so I can put more on my plot. And so what we want to do with this guy is we can cool this guy to 5 microkelvin in like 100 microseconds. So we could show that we can do this in our PRX paper. And we could hopefully get perspective space density of 10 to the minus 7, increasing the molecule number into this guy. And what we hope is for complete unity transfer. So we want to put cross dipole trap on here, and like I just have a little cartoon of like the blue detuned MOT, and then we can apply cooling at the same time, and hopefully we get all of our molecules sucked into a nice dense sample here. And so if we're aiming for like a trap oscillation frequency of like 250 hertz, we could be able to get to a phase space density of 1 times 10 to the minus 5 in a cross dipole trap. And this is like what we're going to like start sprinting to as soon as we get back. But we have one more interesting thing. So we kind of talked about the ground state cooling with GMC here. But one more thing we can talk about is this narrow line MOT going on over here to the left, right? So this guy has a very narrow line width. It's a 2-photon transition here. We can actually use this on a type 1 transition completely. So we can eliminate the dark states and just use that very, very low Doppler temperature that should get you to recoil limit. Okay. Now, this slide looks horrible. I don't want to scare people away. The problem with doing this, though, is the Frank-Condon factors to the state are not very good. Okay. So if you actually want to drive this transition, you actually need to start repumping all the way up to V2 if you even want to scatter about even 100 photons. Okay. So this looks terrible, and you're like, Justin, how are you going to do this? Well, we're going to turn on microwaves and all these transitions, and we're going to repump all of them. Yep. We're going to brute force it. We're going to do exactly as you expect. And I'm going to show you that we actually do this with some data. And then everything looks hunky-dory. Well, unfortunately, the parity splitting in this state is sub 100 kilohertz. So as soon as you turn on this laser, you actually open decay to N3 as well. So this is looking very dismal at this point. It's like, oh man, do you want to try this narrow line trap? Man, you're really pushing it. But I will say that we have every single one of these lasers in-house pumping these transitions, and we have all these microwaves on repumping all these manifolds. Okay? And so to repump these manifolds, the first thing I just want to draw attention to is this green trace. So this green trace was the lifetime of the YO dual frequency MOT about a year ago. And it was actually always limited going into these N0 and N2 states on V1 and V2, okay? Because these guys didn't have, these guys were not repumped. So one day in group meeting, we had a crazy idea. It's like, what happens if we just try sweeping the microwaves over these vibrational manifolds, coupling N0 and N1? So we do this, so we sweep it at 50 kilohertz, and we see something interesting. Oh, wow, okay, so our lifetime of our MOT just went up to 97 milliseconds. Okay, well, let's keep going. Let's sweep it over N1 and N2 up here at 46 gigahertz. We can dither this guy. And it also increases to 97 milliseconds. Okay, well, that's great. Now we can sweep everything all at once at all times. And now our lifetime went up to 215 milliseconds. And so the lifetime of our dual frequency MOT went up by a factor of 3.6 just by simply sweeping the microwaves over these rotational manifolds, which is great. And I want to say like this technical improvement really allowed, 5 minutes. Yeah, 5 more minutes, perfect. This technical improvement really allowed us to go back to that blue detune MOT. Because now we can hold the blue detuned MOT to our vacuum lifetime. Because the scattering rate on the blue detuned MOT is a factor of 3 lower than our dual frequency MOT, which is fantastic. So all these things kind of worked out. But the next thing we need to do is spectroscopy on the delta state. So what you're looking at is spectroscopy from F0 to F1, from the ground state to the excited state. And this beat note is just an offset phase lock to strontium, which is pretty fortunate for us. They have to do all the hard work, but we can just offset phase lock to them. And what you're looking at is depletion spectroscopy. So we turn off a repump, and then we hold this in gray molasses, and we drive transitions while leaving microwaves on attenuated. And then we just look for depletion of the molecules. Well, this is pretty interesting. So at an ISAT of 1,000, we see some weird structure appearing in the wings. Okay, well, let's just keep lowering the intensity and see what's going on. So we lower the intensity more. Now we definitely have some structure appearing in the wings. So we have 2 dips appearing and then like a central dip. Okay, well, I don't quite know what's going on yet, but let's just keep lowering the intensity, right? Let's try to get the structure out of here. And so we can lower to an intensity of 139. And now we really see something quite interesting. So now we see multiple dips appearing on the wings over here on the left and right. But what we really see, which is quite interesting, is we see a sub 100 kilohertz doublet that matches exactly the parity splitting in the delta state. That was predicted many, many years, decades ago. So this is what our current guess of what this guy is going on. And then what we think the wings are is actually most likely Zeeman splitting in the excited state. So I just drew a little cartoon here. So we have the splitting between the parity states. And this is what we think. So as soon as we saw this data, we actually re-zeroed our offset field. And then we retook all that blue detuned MOT data, and we have not gone back quite to the narrow line MOT. So that's basically what I want to cover at this point. This is me. This is the postdoc in the experiment, Dr. Agarwal. This is the other grad student. And then June is, of course, our PI. So thanks for listening, guys. Yeah.
Yeah. Have you tried simultaneously having a dual frequency and a loop MOT? And what I mean by that is just have dual frequency address things like, say, your ground and the free and loop is unit on the other.
I did try this. I did try it for about an hour. And then I was like, forget this. I'm just going to keep moving on. But these are exciting things that we talk about, like maybe repumping some ground state manifolds with a dual frequency mechanism. And then, because we can arbitrarily put as many tones as we want, right, over these guys, and checking each one, and it's a very interesting possibility, and I completely agree.
You have strong spring constant as well.
Yeah, exactly. So the spring constant should start increasing, right, at that point, right? So you're not completely relying on that subdoppler mechanism, removing that excited state population. So particular hyperfine manifolds might be able to scatter those position-dependent photons. Yeah. 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 Yeah, so it's extremely sensitive to beam pointing, I would say. This is something that we really have to take care of now. Even a small, so the dual frequency MOT's not so sensitive, but if we have any mismatch in the pointing, because we recycle our beams on our experiment. So we found that even a slight mismatch would completely distort it because that spring constant is so small, right? So if there's any intensity imbalance in this guy, it's very, very sensitive. For intensity, we haven't really scanned out like cranking down the intensity or like attenuating it, but that's a very interesting thing to check out. Yeah.
You have a question up here.
Yeah.
I wonder, could you explain like
Yeah.
why when you switch the loading efficiency from a MOT to ODT can be increased by that much? Like you point unitary conversion.
Yeah.
By changing into like a cross ODT.
Yeah, so the whole point is if the cloud is very large compared to like your dipole beams, there's not really a position-dependent force for these guys to gently kind of filter in towards the center while you have your cooling beams on, right? And so these guys are just in gray molasses and they're just randomly walking around. And so what you want is you want your cloud small enough that you can turn on just a very gentle dipole beam. So these guys don't wander out away from your trap. And if they're wandering, they're going to be simultaneously cooled. So they're always going to be attracted to the center. And then as soon as they get to the center and they're very cold, they're going to suck right into the trapping volume. Yeah. Yeah.
If there are no more questions, we'll thank our speaker again.
Yeah.